paper is called Energy Efficient or Opportunistic Routing-Based MAC Protocol for Underwater Sensor Networks. Okay, this is the outline. And underwater sensor networks uses are in expansion. Research of ocean conditions, pollution detection, assisted navigation, fishing. We all recall what happened with the tsunami some years ago. We want to know what's happening in the water. And what is wireless sensor networks? Okay, that's wrong. Basically works with a sink and many sensors sending the information to that sink, sometimes directly or sometimes through a forwarding process. And this paper is going to talk about that forwarding process. Okay, the big thing we have is the terrestrial wireless sensor networks. We have been using them for quite a long time, and we see that we can use some of that technology. The access media is air, and the transmission technology is radio frequency. But in the underwater wireless sensor networks, we are using water, and we are using acoustic waves, because radio frequency cannot propagate very deep into water. And that brings us new problems. High propagation delays. Unreliable wireless links is in the water. We cannot control the media the same as in wireless, in terrestrial examples. And low data rates, and the transmission energy is really bigger than the reception energy. We are talking about maybe 25 to 1. Okay, the motivation of this paper, we can see here what happens with the time division median access in wireless sensor networks. If we have 4 nodes and they want to transmit at the same time, we just have to schedule them, and we forget about the propagation delay because it's so small in sensor networks. But in the underwater sensor networks, we have a problem because we have to take into account the distance. For example, here we have some nodes to a different distance. That will mean that the signal, the data are going to reach the sink at the different times. This is one example where if we don't have into account the propagation delay, they are going to come to the sink. There is going to be a collision. And here is an example of a good scheduling where if we take into account the propagation delay, we can manage to make them arrive at the sink without collision. Okay, first we have studied some related work on the topic. The first one is XOR, extremely opportunistic routing, and is for terrestrial sensor networks. Okay, the method is, the sensor broadcasts the packet, and then it learns the successful receivers, and only then chooses one of them as a forwarder. The merits of this is that the delay the forwarding decision allows to try multiple links concurrently, and you can choose the best one, and so the progress of the transmission will be high. But the problem is this system has no scheduling, so the collisions may appear in heavy load environments. When we have many sensors, they don't know when to transmit, they want to transmit, collisions. The second, DOTS. delay-aware opportunistic transmission scheduling. This is an example of underwater sensor networks. And the method is to build a delay map with passively obtained local information. The neighbors will propagate the delay maps and the expected transmission schedules. And with that method, we can make an intelligent transmission scheduling with it. The merit is that it increases the chances of concurrent transmission by reducing the likelihood of collisions. But the problem is it uses ready to send and clear to send packets to avoid the collision increasing and thus increasing the time for the transmission round, because we have these two packets and that increases the delay. And it doesn't consider unreliable links. That happens a lot underwater. Okay, now we go to our design, the protocol design. Okay, should a node broadcast a packet or wait to avoid collisions with neighbor contenders? That's the question. And what we are going to do is we assign probabilities of success to the transmission events. First, we are going to describe some steps, and the first step is to build the ERG, Event Relationship Graph. It's a graph to describe the possibility of conflicts among neighboring nodes. Okay, we are using all possible events and the relationship between them. You can see in these tables that we don't have so much time to build this graph. And this is the result of the graphic result of that graph. Here the circle are the events and the arrows are the relationship. This is a node and these are the possible forwarders. And the idea is that the packet will be forwarded through one of the branches, but we want to choose the right one. The second step is to determine the time and duration of each event. Here we have seen the events, but we have to know how much time that state longs. And we are, sorry.
Assume that all the nodes are synchronized in time. That is, my timestamp is
no.
The same time base as yours or not?
No, they don't know each other. You imagine in water, it's very difficult to synchronize because that requires a lot of battery. Okay, the third step is to build the overlap table. Okay, with all the data of the duration of that we have seen before, with all the data we have from the nodes, we are using an algorithm. We are going to build this table, and in this example, we can see this is a transmission node, this is another transmission node, and they want to transmit at the same time. And the blue one cluster will interfere with the red one if the overlap table says so. And in those cases, we will have a problem. If we get these problems, we know when these problems happen, we can stop transmitting, and then we avoid the collision. So we use the overlap table to calculate the probabilities of collision. The node's probability of transmission success with other contenders transmitting too. And the fifth step is to design the metric to determine if a node can send its packet or has to wait a random backoff time based on the probability of data arriving on time and energy consumption. What we are using, the metric we are using is the value P, meaning the expected probability that the packet will be received at sync before the deadline. When the deadline D, when the node S is transmit at time T1. And the energy consumed is the total expected energy consumption node to sync when node S transmit at time T. Okay, so the important values for us are the throughput and the energy. And that means that if the value of P divided by E is better, we will decide to transmit then for that T. Okay, the evaluation, first, the validation study. Okay, basically we have made some assumptions to make the problem be not as complex to compute. And the first part is to evaluate the accuracy of that approximation. Okay, I'm sorry. So the approximation is to ease the computational complexity in step 4, the step dedicated to calculate the probabilities from overlap table, compared to not doing the approximation. Okay, then the performance comparison. We are going to compare our work with the other two we have seen before. For that, this is the grid topology we are using, and we can see this is the sink, and this is the nodes, the source, basically sensors. These are sensors too that will be acting as forwarders. And the source nodes send packets following a Poisson distribution. Okay, first thing, we compare the throughput in two cases, with 7 nodes and with 16 nodes. Let's call this light load and heavy load. The x-axis is the period of traffic load generated by source nodes, and that's the 50 minutes. Okay, and the second thing important is the lifetime comparison. That is the operation time till first node failure due to the battery depletion. This is very important because we are talking about water. It's not easy to access these sensors, so this should be a key factor when designing these kind of networks. And the conclusion is just what we pursue is an opportunistic routing based MAC protocol to cope with the high propagation delay and unreliability of underwater sensor networks. And what we are using is the event relationship graph to integrate the OR, opportunistic routing approach, with the spatio-temporal uncertainty. That is what we have seen before, the problem with having different delays makes the packets arrive the sync in different times. And then calculate the collision probabilities in order to avoid them, and thus improve the throughput and the energy consumption.